Okay, for our next speaker, let me introduce Professor Yi Cui. Yi is an associate professor of material science and engineering here at Stanford University. He also has a joint appointment at SLAC National Accelerator Laboratory. And Yi has been a GCEP researcher for quite some time, been very prolific, leads a vibrant research group. In addition to his research roles and teaching roles here on campus, he's also an associate editor of Nano Letters and a co-director of the Bay Area Photovoltaics Consortium, which is funded by the US DOE. And he's won numerous awards during his time here. I'd like to just point out a few. The Wilson Prize, which he was awarded last year. The David Philo and Jerry Yang Faculty Scholar, 2010. The Sloan Research Fellowship in 2010. And was a Global Climate Energy Project Distinguished Lecturer in 2009. So please join me in welcoming Yi Cui.
Thank you, Tom, for the nice introduction. So this is my starting 8th year at Stanford right here. Let me tell you my personal experience on GCEP. So I joined the faculty in 2005. And in 2007, my group has about 10 graduate students and postdocs. You know how the things work in tenure track. Your startup package going down like crazy. And I literally had a nightmare waking up in the middle of the night thinking about how do I feed these 10 graduate students and postdocs. So my first big funding coming in, that's the GCEP funding that really saved my group, allow us to continue doing research in the areas we're interested in. So now let me use the next 20 minutes also to give you an overview of what's happening in a new funded GCEP project on the materials design for grid-scale storage. This project was started in collaboration together with Professor Huggins at Stanford right here, initiated by a graduate student, Colin Wessels. He graduated, and a few students joining in, Maura, Richard, and Hyunwook. They are doing a lot of amazing research on this topic. So let's look at the what do we really need right here. We are talking about energy storage for grid scale. This is because we would really like to integrate wind and solar into the grid. These are the renewable sources. They are intermittent. So they create problems to the grid if you would like to have a lot of them into the grid. So you see this second to minutes, minutes to hours fluctuation in the power. So you need to smooth out that fluctuation. And also when you generate the electricity at a time, that might not be the time you use all of them. You know, you need to store them. You need to have a so-called peak shifting from hours to days. With this in mind, now let's look at what's really needed for grid-scale energy storage compared to the energy storage such as batteries we know about. And what's the difference right here? First of all, you need it to be low cost because the scale of problem you're talking about is too big. And if the cost doesn't meet the requirement, there's no way you can implement this in a large scale. So a good number to look at initial cost from DOE is $100 per kilowatt hour. So you might be wondering, this is too expensive. Our electricity only costs, maybe 10 cents also per kilowatt hour. Why this is $100? That's because you have a battery with a capacity of kilowatt hour. You can use it for many, many cycles. At the end, it's the second parameter you should look at. If you can get down to 2.5 cents per kilowatt hour per cycle, then this might become economic. And let's look at the scale also. You know, we are talking about each of these energy storage plants. You want to have a megawatt to a gigawatt scale. Eventually, adding together, you want to reach terawatt in order to, store enough electricity to regulate the grid. So that's a big scale. I'll give you an example how big that is in the next slide. Lifetime 20 to 30 years, right? Our batteries for your cell phone and laptop, you are talking about 3 years. Now you want 10 times more life because your power plant is 20 to 30 years at least, so you need very long life. There's a gap right there. And cycle life, you want to discharge 5,000 cycles. Well, this is by assuming roughly every day or every 2 days you charge and discharge your watch, you calculate that you need at least 5,000 cycles for doing that. Our battery can only run for 500 cycles for most of them. You need high energy efficiency also. There's so much electricity pumping in and pumping out of these storage devices. If your energy storage is not efficient, then you really waste a lot of power. So these requirements are different from what we are familiar with for the portable electronics, right? For the portable electronics, the first thing you probably think about is energy density. If I charge it out my cell phone, how long can I use it? But for here, it looks like energy density is not the most important parameters, but it is still important in a sense. It can affect the cost profile eventually. So let's look at existing technology for the grid scale. They are not adequate. The biggest pie right here, the biggest one is pump hydro. The area right here really makes pump hydro dominating all other technologies. Just consider you can neglect them. That contribution at this moment. So let's look at the pump hydros. The problem is, let's say the good things first. It's scalable. It's low cost. It's a long life. That's really amazing. You look at this big dam right here, right? You just keep pumping water. That's very, very simple. But you look at what's the downside? It's a location dependence. You probably don't want this in your backyard. And it's a low energy density. It's too low. That's why you need this big lake type of structure right there. And its energy efficiency needs to be improved as well. Well, let's look at the batteries and see what about batteries? Battery is just so far away from meeting the requirement we mentioned in previous slide. If you look at the cost, it's too expensive. This is the cost in the system level. This is not individual cell in the system level. Well, this is a horizontal line right here is the DOE target. All this battery technology are just too, all this storage technology are just too expensive. And looking at the battery, just not enough cycle life. We calculate the cost per cycle, per energy. And this is the target. Pump hydro can meet the target, but other things are really too far away. So if you look at this, you say, if I can improve my battery cycle life, that certainly has an impact to the right-hand side parameters, the cost per cycle. And we also need to think about a way to reduce the initial cost as well. Now let's talk about the problem of scale. Last night I was preparing my slide. I sit down, I do a simple calculation based on how much a lithium-ion battery will produce each year. Let's look at the recent data. Based on the recent data, the yearly production of lithium-ion batteries and can power the grid, giving the power only 40 gigawatts for 1 hour. So if you want to connect with the whole world's grid, it only can only store the electricity for probably 10 minutes also. That's it. We spend a whole year, and everybody can now use cell phone and laptops, all contribute their batteries, and doing the grid scale storage. So that's the problem. The scale is really, really tough. If you think about to get to terawatt scale, you need 30 years of production of lithium-ion battery to get there. So we need really fundamental ways to think about how do we do electrochemical energy storage. The good thing about electrochemical energy storage is energy efficiency is very high. And if you can solve those cost problem, and there's a hope we can use that for the grid scale. Looking at the batteries, this is a basic structure. Let me use lithium-ion battery as an example. You have two electrodes, a negative electrode and positive electrode coating onto a metallic foil. You have electrolyte in between. Looking at this fundamental structure, the materials cost is important. How you make batteries is important. So we need to think about ways to change those things fundamentally. So looking at what things you need to do, this is not a comprehensive list, but certainly you need to look at very low cost, abundant materials to meet the cost and also the scale problem. For the electrolyte, for the separators, for the electromaterials, you need to go from, for example, 500 cycles to 50,000 cycles. We need 100 times longer cycle life. And we need to think about different processing, perhaps even different device structure to make batteries. Now let me talk about the work funded by GCEP. We jumpstart this project using other funding, but now transition into the GCEP funding. This is the materials we work on called Prussian Blue. It's a material known for 100 years. It's a material you use to dye your blue jean into blue color. It's very low cost. Prussian Blue has iron, cyanide group right there, potassium. You see this is all abundant. You might be concerned about cyanide group right here. It does not release a cyanide gas until you go to extremely strong acid, let's say pH 0 type of acidity. It has attractive feature. It has this open framework structure. If you look at the basic structure right here, these are the side of R side and P side. These are the metal iron and iron right there, linked together by this CM bond, having this open framework structure. It has this open channel, this pink color. That's the location you can store iron, you can store potassium, you can store sodium, you can store other ions. If you look at, take one of these cross-section image and look at this. This is the side you are talking about. Looking into the detail, this has the radius roughly 1.6 angstrom. You look at these metal ions commonly used for battery, lithium, sodium, and potassium. They fit in there very easily. So this open framework structure really welcome ions to be inserted. This potentially can create really good materials for high power, fast applications. And you can also tune this material's chemistry. Well, you can use, P side and R side can be iron and iron. You can put in copper, low cost. You can put in nickel as well. You can put in other metal ions to tune its electrochemical potential. So this really allows you to have a lot of knob. You can tune these materials to the degree you really like them to be. So we use a really simple synthesis to make this material room temperature, precipitation very fast. For example, if you want to make a Prussian Blue, you put in potassium ion, iron 3 plus, 2 plus with cyanide group precipitate out. You will produce the nanoparticles of these materials right away. Really simple. You can replace iron with others. You can control what's A, that's potassium or sodium. You can control P or R. So forming this nanoparticle structure. If you look at its performance, something amazing is really there. You measure how you charge up this battery. Let's use potassium aqueous electrolyte. So aqueous electrolyte is good, very low cost. Potassium, very low cost. We know organic electrolyte using lithium-ion battery costs a lot of money. Now you can start to charge up your batteries and then discharge your battery. Now you see one thing, that's the difference between the charging and discharging voltage is so small. This tells you this material is extremely fast. We are using this roughly about 1 hour charging and discharging speed. The voltage hysteresis is down to below 10 milliwatt also. It's very, very hard to find an electrochemical system with such low hysteresis. If you speed up the rate and go from all the way down to 83C. 83C means 1C is 1 hour. 83C means 83 times faster. So you're talking about roughly 40 seconds of charging, discharging. For very big electrode we are making, this is very fast. Hysteresis is actually still considered very, very small for this fast charging rate. But you notice one thing right here. The charge storage capacity you can put in is 60. This is only 1/3 of the lithium-ion battery materials, such as lithium cobalt oxide we use. So in terms of energy density, this is not the materials for high energy density, but we are trying to develop this low-cost material, high-performance materials for the grid scale. That's a different argument right now. And also looking at the structure, this is about roughly at the 1.2 or 1 watt also versus the standard hydrogen. So this is for the cathode and aqueous solution. Now let's look at further. So this is also working quite well for sodium. It has this open channel. Now we change the electrolyte to sodium nitrate, 1 molar, also showing this amazing fast kinetics. So if you will compare this with well-known lithium-ion battery material, very fast materials such as lithium iron phosphate and lithium titanium oxide, the capacitor retention at the top right here for our materials is comparable or better. So with this fast kinetics, we actually do we have done the long-term cycling. Here's the cycle performance right there. After 40,000 cycle, you still have more than 80% of the capacity retention. So you are talking about you have 100 times longer than the usual batteries you are familiar with. This is exactly what you need for the grid scale applications. This can impact the cost profile quite a bit. Now let's look at why these materials are so good. And if you charge and discharge your battery, depending on state of the charge, right here you measure the X-ray diffraction and see this diffraction peak shift. And the degree of shifting is very, very small. We are zooming into this diffraction peak a lot. If you calculate the lattice constant versus the degree of charging right there, and you calculate the strain, is only 0.1%. It's a nearly zero strain right there. That tells you when sodium or potassium ions, in this case is sodium, go into the crystal structure, it just fits so nicely. It does not need to expand the crystal structure or construct the crystal structure that much. If you look at the common lithium-ion battery material you use, carbon or lithium cobalt oxide, you have up to about 8% of the volume expansion right here. Now you're having this nearly zero strain materials. That's the way to guarantee you have very long cycle life without doing other fancy materials tuning. So as I said, this material has very rich chemistry right there. Depending on you choose copper to go in together with iron or the nickel, you can tune its potential, you can do the alloy, you can tune its potential to the position you would like. You can also even choose what's the cation you are going to insert. We talk about sodium and potassium. You can look at the ammonium, you can look at lithium. They have slightly charging potential. When you look at lithium, the charging potential right here is lower. That's because lithium has really strong solvation effect with water, and then to strip off that solvation shell, it takes some energy. Actually, it makes it harder for these crystals to take lithium, so the potential needs to be lower. So what about the negative electrodes? We were talking about the positive. In order to make a full cells, working full cell, you need the right negative electrodes. Ideally, you want the negative electrodes potential is close to 0 watt versus standard hydrogen electrode, because you want to max out the battery voltage. You want your positive electrode as high as possible, the negative electrode as low as possible, without splitting the water. It turned out, and you look at the development of aqueous battery, it's so hard to find aqueous negative electrode. It's just very, very hard. There are not many materials available. Even the available, their performance is just so bad. So we started to tackle this problem. And this is a PPY, a polymer. It can you can do oxidation and reduction on this polymer. Well, it turned out when you do this solid curve right here, you do the reduction right here, you see there's a peak close to 0 watt versus the standard hydrogen electrode. But this material is not good to be as a negative electrode by itself, because when you want to do oxidation, there's this plateau right there on the top, and then this voltage just expand to very large range. Eventually, you look at our Prussian Blue family material right here, and when you do the discharge right here, you will lose a lot of voltage. So the cycle life is very bad. People try to do study on that. Now let's look at what's the thinking right here. We also know supercapacitors, right? You can take activated carbon and to make a supercapacitors. Activated carbon usually start with a potential about 0.25 watt also due to the surface charge state. And then when you charge and discharge of these supercapacitors, and the voltage will change, and it actually has amazing cycle life. But if you use supercapacitors activated carbon mechanism to combine with our Prussian Blue family, the voltage you're going to lose by a lot. And the idea is, when we come up with this idea, is to use a PPY as an additive to tune the electrochemical potential of the activated carbon. Now pull down this whole curve down. So at the end, you make the full cell, you can gain a lot of voltage for your batteries. We actually make it. This is recent data, very new, to show you. Now we can use a trick using sodium boron hydride to actually pull down this curve to minus 0.25 watts. And then we make a full cells right here. This is the full cell voltage. Now you have a 1.2 watt aqueous batteries. very fast, potentially long cycle life. We actually proved that we can do a long cycle life, 1,000 cycles without decay. So this is still going. And also, you might ask the question, let me use 1 last minute to talk about this. Why don't we also design the open framework structure, having the right potential for the negative electron? We actually took this challenge, and a postdoc in the group, Maura Pasta, come up with this idea, really great, and now replace iron with manganese, certainly play with the synthesis. Now we find out when you do the CV measurement, you now see if you use oxidation state of 2 to 3, now you can have materials with potential that's 0 versus standard hydrogen. Or it turned out this one also has very fast kinetics when you do charging and discharging, virtually no voltage hysteresis, very fast materials. We are making full cell right now to testing out the performance of the whole batteries. And I also like to extend this further. This open framework structure is ready to take ions. Then why don't we think about this? Instead of just working on monovalent ions, such as sodium, potassium, or lithium, what about we do divalent? Divalent has the benefit. 1 divalent ion goes in, you can charge 2 electrons. So 1 atom, 2 electrons. That's a really good deal right there. You don't need so many ions to go in. So it turned out this open framework structure is amazing for divalent ion insertion as well. We can do now magnesium, we can do calcium, we can do strontium, we can do barium. Now we have all kinds of batteries now coming out, divalent. We are thinking about trivalent as well in the future. Now let me end my talk by summarizing. We are developing aqueous batteries, new materials, low cost, very fast, high energy efficient to do single valent and divalent batteries. I would like to stop right here. Thank you for your attention. Questions?
Hi, Professor Sri. Thank you for your talk. That's very exciting research. I'm wondering if you could talk a little more about tuning the metals in the metal-organic framework. You showed that pretty quickly, and it looks like you can increase the voltage that way. But what are the trade-offs, and how far can you get with that approach?
The question was, using these metal ions inside the open framework structure, how far we can tune the voltage range. In principle, we can tune the voltage range very big because all these metal ions redox potential is documented in the database. You can use that as a reference. Certainly, when you put it into the open framework, the potential will shift a little bit. Indeed, you can tune it above a water oxidation potential, below a water reduction potential. It's all possible right there. Actually, the problem becomes whether they're going to be stable in water. They're going to split water or not. That's the key requirement right here. So far, the highest one we can get is roughly a 1 to 1.2 watt, and the lowest one is about minus 0.2 watt versus standard hydrogen. Beyond that, you start to split water. So you're expecting 1.2 watt, to 1.5 watt batteries also.
Prussian Blue also is electrochromic. That's
right.
Been known for some years. So there's other energy applications for your research in controlling windows, for instance.
Absolutely, you are absolutely right. The Prussian Blue, when you this family, when you let's look at these 2 pictures. Right, they have 2 different colors right there. You can tune the colors. Yeah. I just wrote a small proposal and using Prussian Blue for the electrochromic window. We'll see. This is within radar right now. Yeah.
Thank you. Looking at the future, if you had to store gigawatt hours, at what voltage would you store? I mean, would you have a huge number of these devices in series, or would you lower the voltage and store stuff at the volt scale, or how would you do that?
So this is 1.2 watt. You would absolutely need multiple of these batteries connecting in series as well as in parallel to build up the current, series to build up the voltage. Certainly, battery management system becomes important later. Oh, like in the Tesla car, yeah. Certainly in the Tesla car, it's more challenging right there because you're carrying the batteries, worrying about bumping into other things to have accident. And this is for stationary storage. I will see the challenge will be less in managing the battery system. Charlie.
Hey, this is really exciting. I had a question about calendar life. I don't know if they still dye blue jeans with Prussian Blue, but I'll go up to San Francisco and buy a really hip pair that's really dark. And then 3 years later, I look like a dad from 1994. So I'm wondering how long this
I'm always worried about somebody ask me, what about calendar life? I look at it, I say, my graduate student they stay here for 5 years. So I don't know. That's a good question. Calendar life is so important. We need to study that. But I also tell you the challenge, like 5 years graduate student life. So maybe I'm the only guy sitting right there for 20, 30 years. So.
Wash your battery.
So it's the other corrosion mechanism, though. I agree. There's many bad things can happen. You have electrolyte, you have electrode, you have all the packaging. You need to take care of that. It's not trivial for 20, 30 years.
Any other questions? Well, I have one last question for you, E. So you showed the 60 milliamp hours per gram. I was curious how close that is to the theoretical maximum for this type of material.
For these materials, the theoretical maximum is somewhere around 60 to 70. So It's already close to that. So something I didn't mention is in the crystal structure of this material, it can trap water inside. So that make our accurate calculation of the capacity becomes challenging. There's a little bit of error bar, doesn't affect any conclusion right here. So we don't know, for example, it's 65 or 62 because of the variation of the water content.
Okay, great. And if there are no more questions, let's thank E one more time. Thank you, E.